Hello everyone. So let's start. So today I'm going to start a new chapter, and here you are going to learn about temperature, kinetic theory, and the gas law. Okay. So to start this, we need to understand some terminology. Okay. So let's start with that. Okay. So the first thing you need to understand is an atom. Okay. So here I show a schematic diagram of an atom, and you can see that in the nucleus. So nucleus is basically the inner part of an atom. So in the nucleus we have proton and so proton. Here you see the proton and neutron. Okay, so here proton are positively charged and neutron are neutral. Okay, so inside nucleus, so this is the nucleus, the inner part is the nucleus, where we have neutron and positively charged proton, and in the outer shell we have electron, and electron are negatively charged. So these are the electron. So this is basically a helium atom. Okay, the diameter of an atom is very small. Okay, and it is 10 to the power minus 10 meter. Okay. Okay, so here you see that. Now the next thing is the atomic mass number. We use A to represent atomic mass number, and atomic mass number is the sum of number of protons and the number of neutrons. Okay, it's basically the number of particles that are inside the nucleus. Okay, number of proton plus number of neutrons. Okay, all right. The next thing is the atomic mass or atomic mass unit. Okay, so atomic mass is established by defining the mass of carbon 12 atom be exactly equal to the 12 U. Okay, so here U means the atomic mass unit. So this U is basically is another unit of mass, and we call it atomic mass unit. Okay, the reference of atomic mass unit is the carbon 12 atom. Okay, and you see that carbon 12 atoms mass is taken exactly equal to 12 unit. Okay, all right. Now now it's not the standard international unit. Okay, and you know that the standard international unit for mass is kilogram. So what is the relationship between the atomic mass unit and kilogram? So this is the the relation. So one atomic mass unit is equal to 1.66 times 10 to the power minus 27 kilogram. 27 kilogram. Okay. All right. So atomic mass unit for most of the atom is very close to um, their atomic number. For example, for hydrogen, so here you see this is hydrogen. Hydrogen atomic mass number is 1, and its atomic mass unit is 1.0078 unit. Okay. Unit means atomic mass unit. Okay, so that's about the atomic mass. And as you know that the molecule and atom are different. Okay, we should also know what is the molecular mass. Okay, so molecular mass is a little bit different, but if you know what is the relationship between the molecule and atom, okay, then it's not too difficult to understand the molecular mass. Okay, so molecular mass is basically the atomic mass of all the atoms in a molecule. Okay, so for example, the molecular mass of oxygen molecule is equal to 2 times the atomic mass of oxygen atom. Okay, that's because you know that oxygen 2 in oxygen 2 molecule, okay, we have one oxygen atom and another oxygen atom, two oxygen atom. Okay, so the molecular mass will be the atomic mass of this oxygen and this oxygen, okay? And atomic mass of one oxygen is 16U, okay, because you see that the atomic number for a for oxygen atom is 16. So the molecular mass of oxygen a molecule is 32 unit, okay? Temperature. So what is the temperature? Temperature, normally we use this symbol, okay, T, capital T, to represent temperature, okay? Remember that in physics 1 we use T for time period, so don't confuse time period and the temperature, okay? So temperature is measure of how hot or how cold an object is, okay? So many properties of matter changes with temperature, okay? Normally most materials expand with temperature. So when you increase the temperature, it expand. When you decrease the temperature, the object or material contract, okay? It's the normal property of most of the materials, okay? So you probably see this kind of spacer, okay? So this kind of spacer in a highway or in a bridge, okay? Or the this also called the expansion joint, okay? So these are actually used to avoid the destruction due to the temperature change. You know that most of the materials expand when the temperature increases, and contract when the temperature is decreased, okay? So for example, during summertime, because the temperature is higher, you expect object to expand, okay? Now to facilitate that, we need some expansion joint, something like this, okay? And during winter they contracts, okay? So this basically use this spacer or the expansion joints are basically used to avoid destruction due to the temperature change, okay? And power lines, for example. So here I have another picture, okay? So power line sags during summer because of the temperature, okay, because of the higher temperature. So you probably if you look this kind of power line during winter and during summer, then you can compare that uh, how the power line expand with the increase or decrease in the temperature, okay? All right. So thermometer is the device to measure the temperature, okay? The most common type of thermometers are the liquid in a glass tube, okay? So you probably already see this kind of thermometer. So this kind of thermometer. Another type of thermometer is this bimetallic strip, normally used in the oven, okay? And in both type, the property used is what you learn here in the last slide, okay? Most of the object expands with the temperature with the increase of the temperature, and contract with the decrease in temperature, okay? So this property basically used in a thermometer, in all type of thermometer, okay? And here this is the most common type of thermometer, okay? And inside this thermometer, the liquid is either mercury or alcohol, okay? Now temperature is generally measured using either Fahrenheit scale or Celsius scale, okay? So the Fahrenheit scale or Celsius scale, and the corresponding unit we use are degree Fahrenheit or degree Celsius, okay? Although they are commonly used, but these are not the standard international unit, okay? The standard international unit is Kelvin, okay? Normally we use the Kelvin scale in science laboratory, okay? And in Kelvin we don't use degree Kelvin, okay? So in Kelvin we just use K, okay? So temperature in Kelvin is, for example, if it is 100 Kelvin, we just write 100 Kelvin, not 100 degree Kelvin, okay? But in but in a degree Celsius or in degree Fahrenheit, we have to explicitly say that 100 degree Fahrenheit or 100 degree Celsius. Okay, so remember that. Okay, now how the thermometers are calibrated. So thermometers are calibrated using the freezing point and boiling point of water. Okay, so you know that the freezing point of water is either 0 degree Celsius in degree Celsius or 32 degree Fahrenheit in Fahrenheit, scale, and boiling point is 100 degree Celsius in Celsius scale and 212 degree in Fahrenheit scale. Okay, so based on these I mean thermometer basically calibrated. Okay, so now here you see that between 0 degree Celsius and 100 degree Celsius, the difference is 100 in this side. Here between 32 and 212, the difference is 180 degree Fahrenheit. Okay, so you see they're different. In in Celsius scale, the difference is 100. In Fahrenheit scale, it is 180 degree Fahrenheit. So the relationship between the Fahrenheit and degree Celsius is this one. So 1 degree Fahrenheit is equal to 5/9 degree Celsius. Okay. Now, how to convert if you know temperature in degree Fahrenheit to degree Celsius? So these are the two equation, okay, we use normally to convert the temperature from one scale to another scale. So for example, if you know the temperature in degree Fahrenheit, okay, so you plug the value here and then whatever you get in the right hand side, it is the temperature in degree Celsius. Okay, so for example, if we know the temperature in degree Fahrenheit is, let's say, 72. Okay, so let's say today's temperature, average temperature is 72 degree Fahrenheit. So you plug the 72 here and do the math, and whatever you get here is the temperature in degree Celsius. Okay. Similarly, if you know the temperature in degree Celsius, if you want to convert it, you just use this equation. Okay. All right. Now, Kelvin temperature is not so common normally, but in laboratory you may see Kelvin thermometer. Okay. So in Kelvin, the freezing point of water is 273.15 Kelvin, and the boiling point is this 373.15 Kelvin. Okay, now again you see the difference between the boiling and freezing point is 100 Kelvin, right? So because the difference between the freezing and boiling point are the same in Kelvin scale and Celsius scale, okay, the conversion between the Kelvin and Celsius scale is very simple. It is this one. Okay, so if you know the temperature in degree Celsius, you just plug here and add 273.15 and you get the temperature in Kelvin. Okay, for example, if let's say the temperature in degree Celsius is 27 degrees Celsius, so in Kelvin it will be equal to 300 Kelvin, 300.15. Okay. All right, so Kelvin scale is also called the absolute temperature scale. Okay, and 0 Kelvin is the absolute zero. That means below 0 Kelvin there is no temperature. Okay, so 0 Kelvin is the lowest possible temperature. Okay, 0 Kelvin, or in degree Celsius scale it is negative 273.15 Kelvin. Okay, this is the lowest possible temperature we can have. Okay, but there is no upper limit of temperature. Upper limit, the highest temperature could be anything, trillion degree Celsius or trillion Kelvin, okay, or even more. Okay. All right, the next thing you are going to learn is the thermal equilibrium and zeroth law of thermodynamics. Thermal equilibrium and zeroth law of thermodynamics. Okay, so to understand this, let's consider two objects A and B, and let's say they are at two different temperatures. So here you see that we have A and we have B, and the color tells us that they are at two different temperature. Okay, so when you place them together in contact, okay, at some point the temperature of both object A and B will be the same. Okay, that is the thermal equilibrium. Okay, so thermal equilibrium means when we have two objects at two different temperature, and if we place them in contact with each other, at some point their temperature will be the same, and this is the thermal equilibrium. Okay, and what about the zeroth law of thermodynamics? Is basically um, another way to define thermal equilibrium. Okay, so it tells us that if we have three objects, and three object A, B, and C, and if A and C are in thermal equilibrium with each other, and C and B are in thermal equilibrium with each other separately, okay, then A and B are also in thermal equilibrium. Okay, so, and it makes sense. You see that if A and C are thermal equilibrium and B are C in thermal equilibrium, because C is common here, so A and B needs to be thermal equilibrium. Okay, so that's the zeroth law of thermodynamics. All right. Now let's talk about the thermal expansion. So earlier we learned that when the temperature of an object is increased, it expands. When the temperature is decreased, it contracts, right? So now let's try to understand it quantitatively. Okay. So here we are going to learn two quantitative equations. One is linear expansion. Okay, so although it's called linear expansion, it could be linear contraction also. And in the next slide, we are going to learn about volume expansion or volume contraction. Okay. All right. So to understand this, first let's consider the linear expansion or linear contraction. And to understand this, let's consider this diagram. Okay. So let's say we have a pipe. Let's say we have a rod. Okay, rod of some material. Let's say iron. Okay, and let's say the length of this rod is L0. And let's say the initial temperature of this rod is T0. Okay, now you add some heat. Okay, so heat. So when you heat, heat means you are increasing the temperature. So when you increase the temperature, let's say you increase the temperature of this object, of this rod, to a final temperature of T. Okay, so initial temperature was T0 and final temperature is T. Okay, so because you see that final temperature is higher than initial temperature, okay, it will expand. And let's say it expand by this amount, delta L amount. Okay, and experimentally we found that this delta L is proportional to the initial length. Okay, higher the initial length, higher the expansion, lower the initial length, lower the expansion. And we also see that it depends on the temperature difference. Temperature difference means, so delta T is basically equal to T, the final temperature, minus initial temperature. So remember that delta means always the final, okay, minus initial. Okay, so this change delta L also depends on the temperature difference. Higher the temperature difference, higher the expansion. Okay, now if I combine these two equations, I can write delta L is proportional to L0 delta T. But if I want to write an equation, I need a proportionality constant, and proportionality constant here is alpha. Okay, do not confuse the proportional sign and alpha. Okay, so this is alpha. This and this are two different things. Okay, so alpha here is the proportionality constant, and it depends on the material. Okay, for iron it is if we have iron rod, it is different, alpha is different if we have a copper rod, for example. Okay, so in the next slide I have a table where it shows about the linear expansion coefficient, or coefficient of linear expansion. Okay, now what is the unit of alpha? So the unit of the standard international unit of alpha is Kelvin inverse, I mean inverse Kelvin. But because it is because it depends on the change in temperature, delta T. Okay, so the value in inverse Kelvin is exactly equal to the value in inverse degree Celsius. Okay, you know that you already see in the last slide that the temperature difference between the boiling and the freezing point in Kelvin is 100, and degree Celsius it's also in 100, right? So because of this, the value of alpha in Kelvin scale and Celsius scale is the same. Okay, so in many textbook you see that okay, so here you see this is the list for coefficient of linear expansion, and the unit is degree Celsius, I mean inverse degree Celsius. But if you convert this value in inverse Kelvin, it's basically exactly the same value. Okay, so that's why in many textbook you see it's in degree Celsius, and in many textbook the same number in degree Kelvin. Okay, remember that you can do that, you can do this conversion, you can write this same thing if your equation, I mean same thing means you can write the same number in Kelvin and degree Celsius if your equation involves a quantity that is equal that is delta T. Okay, if it is only T, you cannot use that. Okay, so if there is a term which is change in temperature, then you can use this. Okay, all right, so uh, yeah, so here we have the equation for the linear expansion or the linear contraction. Okay, the same equation you can use when the temperature decreases. Okay, that time instead of expansion we will have contraction. Okay, other than that is basically the same thing. Okay, higher the length, higher the contraction. Okay, higher the temperature difference, higher the contraction. Okay, all right. So here I have a simulation. So let me show this simulation. So here I have a bimetallic strip. So the orange and blue thing here at 20 degrees Celsius, it's the bimetallic strip. That means we have two metal here. Now, if you bring the burner under the metallic strip, under the metal, you will see that it expands and bends. Okay, now here using the property that we just learned, I mean the object expand when the temperature increases, and based on this property they build the fire alarm. Okay, so let's see how it works. So you see the temperature is increasing, and the object is expanding. So here expanding means it's bending, and you see that based on that property the fire alarm is designed. Okay, all right. Next is the volume expansion. So thermal expansion is basically used only for the solid. Okay, because thermal, I mean the thermal expansion or the linear expansion is basically used for solid object. Okay, because only the solid object can have the length. Okay, the gas or the liquid cannot have the length, right? So that's why it's not useful for the gas or for the liquid. Okay, for the gas and for the liquid the volume expansion is useful. Okay, but I mean, volume expansion is also useful for the solid object. Okay, so volume expansion you can use for all object. I mean, no matter whether it is a solid, liquid, or gas. But for the linear expansion is only used for, or only useful for, solid object. So here you see in the chart, in the table, the linear expansion coefficient is only given for the solid object, not for the, so you see this line is only for the solid. Okay, and there is no linear expansion coefficient for the liquid or for the gas. But for the volume expansion coefficient we have for all, no matter whether it is solid, liquid, or gas. Okay, so what is the volume expansion? It's very similar. Okay, so earlier we had delta L, now it is delta V, and delta V tells us that how much it expand or how much it contracts. Okay, but is the volume, not the length. Okay, so delta V is the change in volume, V0 is the initial volume, and delta T is the change in temperature. Okay, and similar to alpha, here it is beta, and beta is the coefficient of linear volume expansion. Okay, alpha was coefficient of linear expansion, beta is volume expansion. Okay, the same thing for the unit. In standard international unit is inverse Kelvin, but because here we have delta T, so no matter whether you use I mean inverse Kelvin or inverse degree Celsius, it's the same thing. Okay, for a uniform solid object, beta is approximately equal to 3 alpha. Okay, so here you see is exactly 3 times the linear expansion coefficient. So it's little different. Okay, it's little different. Okay, but it's approximately is the 3 times the alpha. Okay, all right. So in the last 2 slides at the beginning, I told you that the expansion, I mean, most of the material expand when you increase the temperature and contract when you decrease the temperature. So it's the behavior for most of the object or the material. But there is some exception. Okay, and water is the expansion. Okay, I mean exception. So water behaves differently than all other materials. Okay, water behaves normally when the temperature is above 4 degrees Celsius. Okay, so after 4 degrees Celsius, it's normal. Water behaves normally. Okay, but between 0 degree and 4 degrees Celsius, it behaves opposite to the normal behavior. Okay, so you know that object or materials expand when you increase the temperature. So here you see after 4 degrees Celsius, as you are increasing temperature, you see that it is increasing, the volume increasing. Okay, so after 4 degrees Celsius, there is no problem. But below 4 degrees Celsius, you see that when you are increasing temperature from 0 to 4, you see that the water is contracting, I mean, decreasing the volume. Okay, so you see it is going down. Going down means decreasing the volume. Okay, so water behaves differently between 0 degrees Celsius and 4 degrees Celsius. Okay, now if we plot the same graph, okay, but for density. Okay, so density is mass per unit volume. Okay, so volume is in the denominator. Okay, so it's basically, so density normally use rho. Okay, so this is density is equal to mass per unit volume. Mass is constant, V is the volume. So if you change if you draw the same graph, I mean this graph, but now density versus temperature. Okay, so the graph will be something like this. Okay, so here you see that at 4 degrees Celsius, the density is higher, and it makes sense because at 4 degrees Celsius, the volume is lower. And because the volume here in this equation in the denominator, so at 4 degrees Celsius, the density is higher. Okay, as the temperature is increasing, density is decreasing. Okay, after 4 degrees Celsius. but between 0 and 4 it behaves oppositely. Okay, and this is basically place for the underwater life. Okay, fish and all other underwater aquatic lives can survive because of this exception behavior of water. Okay, so you know that during winter, when the lake or the river freezes, okay, because of this property, because the volume is lower at 4 degrees Celsius, I mean the density is higher at 4 degrees Celsius. Okay, when the top of the river or the lake freeze, okay, still there are water under the ice at 4 degrees Celsius. Okay, so because there are still water under the ice at 4 degrees Celsius, all the aquatic life and fish can survive. Okay, so that's basically a blessing for them. Okay, now the last thing for this lecture is the thermal stress. Okay, earlier in physics 1 we learned about the Young's modulus or elastic modulus. Okay, and you remember probably that we had this equation, okay, for the tensile stress. Okay, so I'm not going to discuss about the tensile stress here, but I need this equation, okay, to talk about the thermal stress. Okay, so if you forget it, please go back to chapter 9 and review what is the tensile stress. Okay, so here it is delta L is the change in length. Okay, here E is the elastic modulus or the Young's modulus, F is the force, A is the cross-sectional area, L0 is the original length, and F over A also called the stress. Okay, in chapter 9 we call it either tensile stress or compressional stress or shear stress, something like this. Okay, so let's say now we want to define the stress, but due to the temperature change. So if the stress is due to the change in temperature, we call that kind of stress as thermal stress. Okay, so now to get this, we have to first solve this equation for F over A. Okay, so F over A, if you solve this equation for this, it will be something like this: E delta L over L0. Okay, now delta L is I mean, for thermal expansion, we know that delta L is equal to alpha L0 delta T, right? Now, if you substitute this delta L for the linear expansion here in this equation, you see that L0 cancel out. So let me do it. L0 E alpha L0 delta T. So you see L0 cancel out. We have E alpha delta T. Okay, so E is the elastic modulus, alpha is the linear expansion coefficient, and delta T is the change in temperature. Okay, and this is the expression for the thermal stress. Okay, all right, so I'm going to stop here. In the next class, I mean in the next lecture, I will be talking about the kinetic theory and the gas laws.